In the previous topic, in the previous class, we have derived the equations of motion for rigid body in translation only. And we considered two different cases of translation, that is rectilinear translation and curvilinear translation, and we derived the equation of motion. Now, in this class, in this part of the video, we will talk about the rotation of a rigid body about a fixed axis. This is pure rotation, so it's only rotation, no, it's not combined with translation. Okay, so in this part we'll derive the rotation equation of motions for rotation about a fixed axis, and in the second part of this video we will do the same thing but for the general plane motion of a rigid body, and for that we will derive the equations of motion. Okay, so but that's in the part 2. For this part, let's talk about the planar kinetics of rigid body undergoing rotational motion. So we start with reading quiz. In rotational motion, the normal component of acceleration at the body's center of gravity is always, and we have 4 options. In this question, it's actually asking us that if the rigid body is to be rotated from its center of gravity, from its center of mass. So that is the center of mass is the point of rotation. Then what is the normal component of the acceleration? And if the body is to be rotated from center of mass, then the normal component is 0. So the correct answer is A, 0. Second question, if a rigid body rotates about a point, the sum of moments of the external forces acting on the body about point O equals which of the following? And the correct answer is I0 alpha, which is option B. So when a body is rotated about any point, then sum of moments about that point of rotation is equal to moment of inertia about the same point of rotation multiplied by the angular acceleration of the rigid body, which is alpha. We will go through the derivation and you will see these solutions of this reading quiz in the lecture. So let's talk about the application. What are the applications of rigid body undergoing pure rotation? So this is the example of the crank oil pump rig. So the crank on the oil pump rig, you can follow my cursor. So this is the crank undergoes rotation about a fixed axis caused by driving torque M from a motor. As the crank turns, dynamic reaction is produced at the pin. So it's talking about this pin. This reaction is a function of angular velocity, angular acceleration, and orientation of the crank. In other words, this reaction depends on theta, omega, and alpha. So if the motor exerts a constant torque M on the crank, does the crank turn at constant angular velocity? So what do you think about it? If the motor torque is constant, will the angular velocity be constant? And is it desirable for such a machine? In order to answer such questions, you should have some understanding about how the oil pump rig works. That's why I have this YouTube video link in the slide, which you can also, which opens to this video. I'm not going to play this video because it's 4 minutes long. I'll just show you first few seconds and then you can watch it. The title of the video is How Do Oil Pump Jacks Work? Okay, so now you can watch the rest of the video at your convenience. But you have seen the machine, it's working. So while this crank rotates, it's in pure rotation, and this rotation is converted into pure rotation of this walking beam, which in turn is converted into reciprocating motion of the piston that draws the oil from the ground and it delivers to the tank via pipeline. Okay, so that's how it works. So this is very practical situation where we need to apply rigid body kinetics for in the equation of motions for the analysis of forces exerted on the pin, as well as the angular acceleration, angular velocity of the crank. Uh, this is one example of the practical importance of the analysis that we are doing. So in this case, if you know the angular velocity of the crank and you know the size of the oil pump rig, then one can calculate the angular velocity of the link BCE, which is this link, horizontal. From that, one can calculate the reciprocating velocity or the linear velocity of point D, which is connected to the piston. Now, if you know the reciprocating speed of the piston, that is velocity divided by time for the piston, if you know the area of the piston and the volume, then one can calculate the oil flow rate, that is how much oil in meter cubes per second or in gallons per minute this oil pump rig delivers. And see, that's very practical information for any oil pump rig. So that information depends on the velocity analysis of rigid body, and this also depends on the strength of the shaft at O, for which we need to apply equations of motion for rigid body in pure rotation. So this is the application of what we are going to do. There is another application of pure rigid body in pure rotation. This machine here is the Charpy impact machine, in which this pendulum is raised to certain height. So when it's raised to certain height with respect to the bottommost position, it has some potential energy. And when it's released, this potential energy gets converted into kinetic energy. And with that high kinetic energy and high mass, this hammer or this pendulum, it hits the object, and it basically it's calibrated to measure the hardness or toughness of the object at which it breaks. Okay, so its angular velocity omega begins to increase. Can we determine the angular velocity when it is in vertical position? On which property of the pendulum does the angular acceleration depend? And you know that angular acceleration of this pendulum depends on the mass moment of inertia of the pendulum and how far the point of rotation is from the center of mass, which is G. So what is the relation between P and alpha? So where P is the property of the pendulum that depends on the angular acceleration, and we will see that equations of motion are useful for this analysis. So let's start with this simple diagram here. So this is rigid body in pure rotation. Now the body rotates in XY plane only, which is the plane of this slide, and the Z axis is perpendicular to this slide and coming out from the screen. Now capital G here is the mass center of the rigid body, and O is the axis of rotation of the rigid body. These are different forces which are applied on the body. M1 and M2 are various couple moments that act on the body, and as a result of all these forces and couple moment, the body rotates counterclockwise with some angular velocity omega and some angular acceleration alpha. And if you look at the path followed by the mass center of the rigid body, then it's a circle, or it's a circular path or arc. So now for this problem also we follow the same strategy as we have followed previously. We need to draw the free body diagram and indicate all the forces that are applied to the rigid body, and we draw kinetic diagram and indicate the angular motion of the body, angular velocity of the body, angular acceleration multiplied by the moment of inertia of the body with respect to its mass center. Okay. And now in this case the body is not rotated from its mass center, hence we need to consider this vector from the axis of rotation O to the mass center. We call this vector Rg, and the length of this vector is the scalar or the magnitude of the vector Rg. Now in this kinetic diagram we indicate the two components of acceleration because we use normal tangent coordinate system, where tangential axis is tangent to the path followed by mass center, and normal axis is always a point that points towards the axis of rotation, which is O in this case. So this is the resultant normal force acting on the rigid body, which is the combined force of all these forces. Okay, but it acts only in tangential direction. Excuse me. And This is the resultant normal force that acts on the rigid body, which is again the combination of all these forces. So basically what we have done here is we have reduced all these forces to a single force, and then we have projected that force along tangential axis and along normal axis. Now the line of action of the normal axis passes through O, but the tangential axis is at some distance rg from the point of rotation. So when in this case we can apply the same normal tangent equations of motion, that is sum of forces in normal direction is mass multiplied by normal component of the acceleration of the center of mass. However, in this case we will replace this normal acceleration by this term, which is r omega square, where rg is the length of this vector between the axis of rotation and center of mass. Okay, so this is r omega square. This is not new because you know that normal component of the acceleration is v square divided by r, right? In that, and you also know that v is equal to r omega. So in that v square divided by r equation, if you substitute v is equal to r omega, so then it will be r square omega square divided by r. So one r will get cancelled from the numerator, so you will get r omega square, and that's what we have here. Then the second equation is sum of forces along tangential direction is mass multiplied by tangential acceleration, which is m rg multiplied by alpha, where alpha is the angular velocity. And third equation of motion is sum of moments about mass center is equal to mass moment of inertia multiplied by alpha. However, this equation is useful only when the body is being rotated with respect to an axis that passes through G. But in our case, body is rotated with respect to O, so we have to modify the third equation. Okay, so this is just to give you an idea about tangential and normal axis. And then let me bring this slide. Okay, so so this is fine. So now we need to change this equation for equation where we need to sum all the moments about point O, because point O is our point of rotation. So sum of all the external moments about point O, which is obtained from this diagram, is equal to the right hand side is obtained from the kinetic diagram, where it's Ig alpha, that is mass moment of inertia with respect to mass center multiplied by angular velocity, plus this component is called kinetic moment because of the resultant force. So in this example, the resultant force has two components, normal and tangential, but the normal component does not contribute to any moment about O because its line of action passes through O. It's only tangential component that contributes about the moment. So it's this force multiplied by this perpendicular distance between the line of action of this force and point O. So that's why we have this Rg multiplied by m Agt. Okay. Now in the previous equation we have here Agt is, that is acceleration, tangential acceleration is r alpha. So you can replace this Ag here with r alpha. So then this term is r square m alpha. Okay, now alpha is common in both the terms here, so we can take the alpha common and then put the rest of the terms in the bracket. So now it is Ig plus m Rg square in bracket alpha. Now this equation is familiar to us. We have derived this equation in chapter 16. This is the equation of this is the application of parallel axis theorem, that moment of inertia of any body about any point of rotation is nothing but the moment of inertia of that body about the center of mass plus the m, which is mass of the body, multiplied by the distance between the two axes, the square of the distance between two axes. So this whole term is called IO alpha, where it's O stands for mass moment of inertia about point O, and alpha is the angular acceleration. And this is sum of all moments about an axis that passes through O. So this is our third equation of motion. Okay, so now for rigid body in pure rotation, we have three different equations. One is sum of forces in normal direction, second is sum of forces in tangential direction, and third equation is either sigma mg is equal to ig alpha. Use this equation only when the rigid body is being rotated about its center of mass. If that is not the case, then use this equation where sum of moments about the point of rotation is equal to moment of inertia about that point multiplied by angular acceleration. Okay. You will get all these equations in your final equation sheet for the exam, so you don't have to like worry about memorizing it. However, make sure that you understand the meaning and significance of each and every component of this equation. So the procedure for analysis of rigid body in pure rotation is, first step is you define the coordinate system. So use normal tangent coordinate system. Second, draw free body diagram, indicate all the forces. Then draw kinetic diagram, indicate the resultant acceleration and resultant forces in the kinetic diagram. Next step is compute the moment of inertia, either IG or IO. It depends on whether body is rotated with respect to its own mass center or with respect to any other point. And then write the equations of motion, identify the unknowns, and solve for the unknowns. Okay. Use kinematics if there are more than 3 unknowns, since the equations of motion allow only for 3 unknowns. Okay, so that's the procedure for analysis of rigid body in pure rotation.